This episode of Ask Mr. G comes from Hayden asking in chat during class, what would happen if all the gas giants collided? Would there be enough mass if all four of these planets, or maybe three of the four, colliding would generate enough energy and enough gravitational pressure to cause fusion and to become a star? Because Jupiter is often called a failed star, or what we now call a brown dwarf, the boundary between a planet and a star. Because if a planet had fusion at its core, it would produce light and be what we would call a star. In order to have fusion at the core of a star, that object needs to have a mass of about 1.6 times 10 to the 29 kilograms, or about 0.08, about 8% of a solar mass, which is 2 times 10 to the 30 kilograms. So we need a fraction of that mass to have gravity pull hydrogen into other hydrogen and fuse into helium, because one proton and one proton makes helium. Atomic number 1, 1 plus 1, 2. Atomic number 2 is helium. Protons don't like fusing into the same nucleus and forming a nucleus because they're both positive. So you need a lot of gravitational pressure, which means you need very strong gravitational attraction, which means you need a lot of mass. And that's why stars are able to do fusion. And then once fusion occurs, you have a release of energy. These are the four gas giants. Jupiter's mass, 1.9 times 10 to the 27th kilogram. Saturn's 5.7 times 10 to the 26th. Uranus is 8.7 times 10 to the 25, and then Neptune's 1 times 10 to the 26th. So clearly, Jupiter having the greatest mass. And remember, these are powers of 10. These are exponential in size. So even though Saturn and Neptune are 10 to the 26th, and Jupiter is 10 to the 27th, Jupiter is much more massive than Saturn and Neptune, because it's an entire order of magnitude higher. It's exponential. They almost double in size. So how many solar masses is Jupiter, Saturn, Uranus, and Neptune? To figure that out, we just divide by the mass of our sun. When we do that, we just divide the fractions, or the numbers in the scientific notation, and then we subtract the exponents. 1.9 divided by 2 is 0.95 times 10 to the negative 3, because 27 minus 30 is negative 3. For Saturn, 5.7 divided by 2, 0.35 times 10 to the negative 4. Uranus, and then Neptune. Well, these are all in negative exponents. So where we do positive exponents and move the decimal place over to the right that many number of times to make it into standard notation, we're going to move it to the left, because these are incredibly small numbers in terms of solar mass. So incredibly large numbers now becoming incredibly small numbers, fraction of a solar mass. So times 10 to the negative 3 for Jupiter, we're going to move the decimal place over 3 times to the left and fill in any blanks with zeros. 1, 2, 3, decimal point. So 0.0095, a little bit of rounding. Jupiter is 0.001 of a solar mass. Incredibly tiny fraction, even though it's incredibly large, and only 3 orders of magnitude away from the sun. The other gas giants are even smaller fractions of a solar mass. Uranus, Neptune. If everything is added all together, the four gas planets, you only get all four gas giants being 0.00113 solar masses, which is much less than what we need for the 0.08 solar masses to conduct fusion in a large enough object. So there is not enough mass if you could collide all four together. But what if we could add mass? All sun-like stars have a companion. We see this in the nearby nebula, the Perseus Molecular Cloud, nearby being 600 light years away. In this nebula, gas is coalescing under its own gravity, densest pockets form spherical objects and gain enough mass to conduct fusion. Most of this occurs with binary or trinary systems. Modeling from an article on earthsky.org showed that these binary pairs all form initially as wide binaries, and they either shrink or they break apart after 1 million years. Where's our sun's binary twin? NASA's analysis of Kepler 223 a star that has 3 sub-Neptunes. They are smaller than Neptune, but still gas giants, but orbit very, very close, relatively speaking, to their home star. They found that these planets exist in resonance, where their orbits occur in sequential order in a ratio that stays close to a 1-to-1. Their years are locked together. This is a video of the team conducting their research and the modeling of this system over time. A little bit of variation, but you see that these planets stay locked together. So our solar system should have had some kind of resonance with our gas giants, and they should have been closer to the sun. This is a theory called gas giant migration. Our planets formed probably closer to the sun, but have moved away from the sun over time. That means something had to kind of nudge and tug the gas giants. Maybe not enough mass in what was the nebula for the sun to form 2 stars, but a brown dwarf. A star that did not undergo fusion because it does not have enough mass. And the movement of the sun and the brown dwarf in this binary orbit in conjunction with the gas giants probably may have either ejected the brown dwarf out of our area, so broke that wide binary, or put it in an orbit that is so large, elliptical in nature, that we cannot track it because it does not produce light. And the gas giants have all migrated to an outer orbit and lost resonance. So these brown dwarfs, these failed stars, these objects below 0.08 solar masses, but very, very close. What if our sun's binary twin, which could have been another star or a brown dwarf, or maybe another brown dwarf that is now rogue and wandering the galaxy in the opposite direction than all the other stars moving around the Milky Way? What if a brown dwarf entered our own solar system? In order to get the brown dwarf to affect as many of the gas planets as possible, let's aim for the rough midpoint, somewhere between Saturn and Uranus. We'll aim for Uranus, because remember, the distance between the sun and a gas planet doubles as you move into the outer solar system. So Neptune is very far away. Brown dwarf is moving into the solar system and collides with Uranus. The debris is held together by the gravity and eventually moves into an orbit closer to the sun due to its mutual gravitational attraction, where it will then interact with Jupiter, or it could also interact with Saturn. All collide together and cause the formation of a larger object, which is now slightly greater than 0.08 solar masses, with the additional mass of these 3 gas giants. Neptune would move closer in, but still stay now in a own orbit. The inner planets would also probably be forced to migrate further out from the sun, or the sun would move closer and keep everything roughly the same. Ceres, any large objects in the asteroid belt, would probably also be incorporated into the debris, the formation of a new spherical object into the outer solar system. Or, if they do not enter this debris field, they would come crashing into interior solar system and cause a massive amount of destruction. So this new object would gain what we would call an accretion disk. Not so much different than how our sun formed in a nebula. This accretion disk is being pulled, this disk of material, into itself, becoming larger and larger. The closer it is to the center, the faster it's moving, and the more mass it's pulling in on itself. Eventually, this object would start fusion in the core. And when that would happen, strong stellar winds and radiation would be released. And because it's spinning so fast, it has nowhere to go but the poles. And so all this radiation energy is ejected outward in solar flares and coronal mass ejections of plasma into space, but also immense amounts of radiation from the poles. So from a lecture at the University of Oregon, we can look at brightness of stars versus their temperature. And the main sequence stars, like our sun, sit somewhere kind of in a negative linear path. T Tauri stars are AB stars. They are stars that are forming. They are the stars that have an accretion disk and massive amounts of radiation. Again, strong stellar winds and high surface activity, which is what you would have now in the location of Saturn in the outer solar system if a brown dwarf, either the sun's twin or a rogue brown dwarf ejected like maybe ours may have been, enters the solar system at the right point. So if you could see what was going to form at nighttime, if you're facing away from the sun, be uninhabitable because of asteroid impacts and debris from the formation of the secondary object. But as you're facing away from the sun, facing out into the further part of the solar system, you would see a new T Tauri star. This is all due to sending a brown dwarf into the rough area of the outer solar system and causing a collision and having just enough mass to cause fusion. There is not enough mass alone in the gas giants to cause a star to form, but there may have been a twin in Sun's previous history, or if it was ejected or still exists, what would happen if it collided with the other planets? Got any other questions? Let me know. I'll see you later.